Welcome, class. Go ahead and grab a seat. I'm absolutely thrilled to have you all here for today's explainer. We are diving straight into Physics 101, and today we're going to uncover the invisible, microscopic electrostatic forces that literally hold the matter of our entire world together. We're going to break down the history, the discovery, and the actual mechanics of electric charges.
Here is our syllabus for today's lecture. We'll start with the spark of everyday life, walk through the history of electric charge, then look at the mechanics of electron transfer, conductors and insulators, and the basic properties of charge. And stick around, because we're wrapping up with a quick Physics 101 pop quiz.
All right, Part 1, the spark of everyday life.
Now, to ground these physics concepts, let's start with something you've all definitely experienced. Have you ever pulled off a synthetic sweater on a really dry winter day and heard that sharp crackle? Or maybe you felt a sudden, annoying jolt when grabbing a car door handle. Or, on a much grander scale, you've stood in awe watching massive bolts of lightning during a thunderstorm. Have you ever stopped to wonder what exactly is happening behind the scenes to cause those shocks? Well, all of these everyday phenomena occur because electric charges naturally accumulate on insulating surfaces through everyday rubbing and friction. When those charges build up enough, they suddenly discharge, sometimes right through our bodies, or, in the case of lightning, straight across the atmosphere. It's what we call static electricity. And static simply means that it's a charge that isn't moving. It just sits there, completely still, until that sudden, surprising release. Moving on to Section 2, the history of electric charge. To really understand how matter acts like an electrical system, we need to trace this back historically. Our journey actually begins way back around 600 BC in ancient Greece with a philosopher named Thales of Miletus. He discovered that if you rubbed amber with wool, it would suddenly attract light objects like feathers. Fun fact for you, the modern word electricity actually comes from electron, which is the Greek word for amber. Fast forward to the 18th century, and it was the American scientist Benjamin Franklin who officially gave us the names for the polarities we still use today, positive and negative. And finally, culminating in 1912, Millikan experimentally demonstrated the quantization of charge. This image brilliantly illustrates the specific rubbing experiments early scientists used to classify charge polarity. Notice how when they rubbed two glass rods with silk and brought them close together, the glass rods pushed away from each other. But if they brought a plastic rod rubbed with cat's fur near that same glass rod, they'd attract. Through these incredibly meticulous observations, they proved a fundamental rule of the universe: like charges repel and unlike charges attract.
Which brings us to Section 3, the mechanics of electron transfer.
Okay, let's dive into this. What is actually happening down at the microscopic atomic level during these rubbing experiments? Well, step 1, atoms naturally have their electrical charges exactly balanced, making materials electrically neutral. But in step 2, when we physically rub two materials together, like the glass and silk, that friction literally strips some of the less tightly bound electrons from one material and forces them onto the other. So step 3, this electron transfer leaves one object with a deficit of electrons, making it positively charged, and the other with an excess, making it negatively charged.
The crucial takeaway here is what we define as the polarity of charge, which is simply the property differentiating positive and negative electrification. Notice that when Franklin named these, and when we observe this transfer today, we realize that no new charge is ever created out of thin air. It is just moved from point A to point B. Actually, if you take that electrified glass rod and touch it back to the exact silk it was rubbed with, their opposite charges will pull right back together and completely neutralize each other. Let's move to Section 4, Conductors, Insulators, and Electroscopes. Take a look at this summary table, as it is absolutely vital for understanding electrical resistance. To wrap your head around complex charge flow, think of it like water moving through pipes. Conductors, like metals or the human body, are like wide open pipes that allow the water, our electrons, to move comparatively freely. Insulators, like glass, plastic, or wood, are like pipes packed full of thick gravel. They offer high resistance and basically stop the flow. And semiconductors? They sit right in the middle, offering intermediate resistance to that movement. You can really see the stark side-by-side contrast in how these materials react. When a charge is transferred to a conductor, it readily distributes over the entire surface of the material. By contrast, if you put a charge on an insulator, it remains stubbornly fixed exactly at the same place you put it. This is exactly why a plastic comb gets staticky when you run it through dry hair, but a metal spoon doesn't.
Any charge on that metal spoon just flows right through your conducting body and straight into the earth.
Now, to prove these theories, early physicists couldn't just hook up a digital multimeter. They had to rely on historic detection tools like the gold leaf electroscope. It's a beautifully simple apparatus. You have a vertical metal rod housed in a box with two incredibly thin gold leaves hanging at the bottom. When a charged object touches the metal knob at the top, the charge flows down the conductor to the leaves, and because like charges repel, the leaves push apart. The wider they diverge, the greater the amount of charge.
All right, Section 5, Basic Properties of Charge. Now that we've seen how charges transfer and flow, we need to lock in the three absolute universal laws governing electrostatics. First is additivity. The total charge of a system is simply the algebraic sum of all its individual point charges. Second is conservation. The total charge remains absolutely constant in an isolated system. And third, quantization. All free charges are exact whole number integral multiples of a basic unit, meaning you can't have half the charge of an electron.
I really want to emphasize this core principle. As this quote highlights, within an isolated system, the total charge is always conserved. This means you literally cannot create or destroy net charge in a closed loop. You can only redistribute it. When you rub two bodies together, whatever charge one body gains, the other loses in perfect exact balance.
And finally, Section 6, our Physics 101 pop quiz.
Let's see how well you've absorbed today's foundational lecture. I have two quick questions for you. First, who first observed frictional electricity way back in 600 BC? And second, based on our material definitions, what specific type of material heavily restricts the movement of charge? Take a second to think back to our historical timeline.
Let's see how you did. The answers are Thales of Milos, who noticed amber attracting light objects, and insulators, like plastic and wood, which offer high resistance to charge. If you nail both of those, congratulations! You are building an incredibly solid foundation in basic physics.
We've learned today that these electrical forces are basically all-pervasive. They aren't just parlor tricks. They hold atoms together, govern chemical bonds, and shape our entire physical reality. So I'll leave you to ponder this. If these seemingly simple forces of attraction and repulsion govern everything from a tiny static shock on your sweater to the very structure of matter itself, what more could we learn by fully mastering them? Thank you so much for joining me for this explainer, and class dismissed.